All right, are we good to go on the cavitation?
Yeah, it looks great.
All right, folks, what we have here is I've got a PowerPoint presentation and we have our model MF200 CAV cavitation trainer, which is going to help us really understand this whole concept of cavitation and pseudo-cavitation. And so what I'd like to first and foremost begin with is if you take a hydraulic pump and you divide it through, or let's just say it's a 360-degree circle, and you divide it 0 to 180 degrees, the one side of it is the intake, and the opposite side, of course, is the pressure side where you obviously produce flow. The intake side of a hydraulic pump works on a completely different set of physics to the discharge side of the pump, completely different set. And I think it's the most underappreciated component of a hydraulic system. I do a lot of blogging, and I've been talking a lot about this whole concept of points of reference. Now, let me just give you sort of a broad overview of what that sort of means. Well, let's just bring up a pump here, and I'll come back to that. So here's a hydraulic pump. This is the intake, and the other side is the discharge. So let me just start here. Now, proactive maintenance obviously means that you're on a routine schedule, you're checking certain operating parameters of a hydraulic system. When a manufacturer of a machine purchases a hydraulic pump from a pump manufacturer, the pump manufacturer gives the machine manufacturer a specification on the pump. And part of that specification is that the pump must not exceed X number of inches of mercury at full flow. All right, so let me just say that again. The manufacturer purchases a hydraulic pump from a hydraulic pump manufacturer. So the machine manufacturers, design engineers purchase the pump. The manufacturer of the pump tells the machine manufacturer, the manufacturer's engineer, that when they start the pump, they should go to the assembly line or down onto the prototype unit, and they need to make sure that the inlet restriction is well within the maximum inlet restriction recommended by the respective pump manufacturer. So let's give that a number. Let's say, this is a gear pump on the screen. Let's just say a gear pump, by rule of thumb, the maximum inlet restriction at normal operating temperature, which is about 135 degrees Fahrenheit, is 8 inches of mercury. It can cold start to 10, but it cannot exceed 8. Now, when I say well within, you have to realize that if you go out to the assembly line on a prototype machine and the weather's reasonable, let's say ambient temperature is 80 degrees, and you're at 7, you have to realize if this machine's going to go and work in a cold environment, it's going to go way over the top when the oil is cold. So it must be well within that number. So the engineer does two things, or is supposed to do two things. One, first, I've established that I'm well within the manufacturer of the pump's recommendation. And two, when I do that, I will establish the pump's inlet restriction point of reference. So let's just, again, go back to the 8 inches of mercury on a gear pump. So the manufacturer says 8. Let's say I start the pump up on an assembly line and I have 4 inches of mercury. 4 at 135 degrees Fahrenheit. I've done two things. One, if I've established that I'm well within the operating parameter given by the pump manufacturer, but two, I have now established that pump's operating point of reference. For the rest of time, that pump must operate at no more or no less than 4 inches of mercury at normal operating temperature. Now, here's the bad news. In my career, let's just say in the past 4 decades, have never seen a hydraulic pump that has something on the intake where I can check inlet restriction routinely. It should be done every 30 days based on an 8-hour shift to make sure that I'm trending on the point of reference line. All right, I've never seen it. Number one. Number two, I've never seen a point of reference. In other words, for those of you out there that are working with manufacturers, ask them. See if you can find an inlet restriction point of reference. Now, here's what unfortunately has happened. When the manufacturer of the machine develops the service manual, what I find interesting is they take the manufacturer of the pump's information, specifications, and they photocopy them and they put them in the manufacturer's service manual. So what have you just received as a maintenance person? You've just received the specification that the manufacturer was intended for the engineer, not for the maintenance person. In other words, what you'll read in that service manual is that the inlet restriction must be no more than 8 inches of mercury. Well, that's not what you want. What you want is the point of reference. Now, I can go on about points of reference. When we talk about proactive maintenance in hydraulic systems, let's go, just let me throw it out there. I've never seen a point of reference for case pressure. No point of reference. I've never seen a point of reference for temperature drop across a heat exchanger. No point of reference. In other words, what you'll find disturbing is that most manufacturers, with all due respect, don't know their own points of reference. Now, why is this important? In other words, why do you want to go out there and check the inlet restriction of a hydraulic pump every 30 days based on an 8-hour shift? Well, I did for 10 years of my life, I analyzed hydraulic component failures. That's all I did. Every day I took pumps apart, looked inside them, and saw why they had failed. So here's the bad news. 75% of open loop pumps, 75%, had either signs of cavitation or cavitation had caused their demise. Isn't that a disturbing trend? If 75% of open loop pumps have signs of cavitation or cavitation that caused them to fail, couldn't that have been prevented if we were checking the inlet restriction on a hydraulic pump every 30 days based on an 8-hour shift? Now, what are you looking at when you look at inlet restriction? Well, if you read books about screens in hydraulic tanks, if you look at the disadvantages of a screen, universally, they'll tell you that you can't check them. I find that interesting. You can put an indicator on a filter head, on a return line filter or a pressure line filter, but you can't check a screen. What does a vacuum gauge do? If there was a place on the pump, on the intake of the pump, where I could check inlet restriction every 30 days, then I wouldn't have a problem looking at the screen. So when you're checking inlet restriction on a pump on a routine maintenance basis, you're looking at a number of things. One is you're looking at the condition of the breather on the hydraulic reservoir, because if the breather starts to plug, it's going to show up as a problem with inlet restriction. You're looking at the viscosity of the oil. You're looking at the speed of the pump is turning. In other words, what if the pump speed ramps up and you don't know that? You'll quickly see it because your inlet restriction will go up. You're looking for air leaks on the intake side of a hydraulic pump. You're looking at everything. It's absolutely critical that we check just that parameter, just based on the fact that 75% of hydraulic pumps are failing, or at least have indications of having failed or have signs. Let's say it contributed to the pump's demise. So let's go back here and let's understand how the intake side of a hydraulic pump actually works. Oftentimes you'll hear people say that the oil is getting sucked into a hydraulic pump. Well, that's actually not the case. Here's an air compressor, and the air compressor is connected to a hydraulic reservoir that is, let's say, sealed, and it's got a tube sticking out of it. Now let's start the air compressor up. And you'll notice that if I compress the air, in fact, you can ask students this question, what will happen if you compress the air above the liquid? They'll tell you, it'll push the liquid out of the tube and it'll flow out of the reservoir. So you see, you've just introduced the student to the concept of push, not suck. push. In other words, if that's exactly how a hydraulic pump works. If the pump is mounted above the hydraulic reservoir, I mean, if it's gravity fed, fine. But let's just say it's mounted above the reservoir. That's exactly what happens. Here's how that works. Look, here's the Earth. It has an ocean of air that surrounds the Earth. Well, a gentleman by the name of Torricelli found a way to measure the weight of that of the air. So let's do that. Let's just weigh it. So we'll take it all the way out into space. We'll just measure it, put it on a scale. And as we know, atmospheric pressure at sea level is 14.7 pounds per square inch. Now, take that 14.7 psi through the breather into the reservoir, and you have 14.7 psi pushing down on the oil. All hydraulic pumps are partial vacuum generating devices. So clearly, if I have a pressure in the pump, or I generate a lower pressure in the pump than I have outside the pump, oil is going to flow. It's going to push the oil into the pump. So you can see this is a very, very delicate part of your hydraulic system, because in reality, relative to your elevation, because at sea level atmospheric pressure is 14.7 psi, but in Denver, Colorado, where you're 6,000 psi above sea level, you're at 12.1 psi. So keep going up and the pump won't work anymore. And that's one of the reasons why we say the manufacturer's job is to make sure that the inlet restriction is well within the specification set forth by the respective pump manufacturer. Because if you're a marginal, you're in trouble if you get into cold temperature 1 and if you go into a higher elevation number 2. So that's how it works. Oil is pushed into a hydraulic pump. A pump is a partial vacuum generating device. It's as simple as this. Here we're going to do an increasing and decreasing volume, meaning this. I'm now going to pull this lever out, creating a vacuum, a lower than atmospheric condition, and the atmospheric pressure is going to push the oil up through the check valve and into the chamber. Then I'm going to go the other way. I'll take the vacuum gauge out, put a pressure gauge in, push it the other way, and now I'm decreasing the volume. So anybody who's operated a porta power, a floor jack, a bicycle pump, that's exactly what you were doing. Now, obviously, you can't have a pump like this in a hydraulic system because the flow is going to be erratic. It's going to, as you know, if you've jacked a car up, it goes up like this. So we have multiple, let's say, pistons in a piston pump or multiple vanes in a vane pump. So here's how it works. In this example, we're going to use an external gear pump. Its name is derived from the fact that the one gear is external to the other, and let's fire it up. So here we go. As you can see, I'm creating a vacuum here. Atmospheric pressure is pushing the oil into the pump. It's coming around the gears and is being pushed out the other side. That's how it works. That's how all pumps work. The only problem is when you look at rule of thumb, because that's really what we go by in the field. You look at the 3 respective pump designs: piston, vane, and gear. The maximum inlet restriction on a piston pump, excuse me, at 135 degrees Fahrenheit is 4 inches of mercury. A vane pump is slightly more tolerant to high inlet restriction. It goes to 6 inches of mercury, and of course a gear pump sits at 8 inches of mercury. The critical thing is to know the point of reference. All right. So let's move over now to the cavitation simulator. And let's talk about how this works. All right. All right, so let's go ahead and just introduce you to the cavitation simulator. Now, of course, instructors, we all find ways to try to get students to understand things. And if there's one thing that always challenged me, or many things, of course, do, but the one thing that's very difficult to help students understand is cavitation. Very difficult. To explain it is difficult. And it's not difficult because it's cavitation. It's difficult because what is it? Is it aeration or starvation? In other words, when I ask students, do you know what cavitation is? Some of them will say, yeah, sure, so the pump's starving for oil, okay? Others will say, oh no, you've got low oil level, so the air is going in. No, they can't both be cavitation. So let's define cavitation. Cavitation by definition is the formation and collapse of gaseous cavities within a liquid. So looking at this tank, it is almost impossible to see that there is 10% dissolved air by volume in this oil. Think of a bottle of pop. If you open a bottle of pop, like Sprite, let's say it's translucent, you'll notice that it goes from clear to bubbles. It fizzes. Do you know that if you, well, let me just finish that point. The reason why the dissolved air came out of the liquid is because you took the pressure off the liquid when you opened or took the top off. Well, think about if you put hydraulic oil in a syringe and generated a vacuum on the oil, it would look exactly like a Sprite or a bottle of pop. It would look exactly the same. So therefore, the definition of cavitation is the formation and collapse of gaseous cavities within the liquid. That's why the manufacturer is so careful about giving a maximum inlet restriction specification, because what it does is it says to me, if you go above that max parameter, then the dissolved air is going to come out of the oil and you've got yourself a big problem. That is, as soon as that little cavity comes out of the oil, it's a happy little cavity on the intake side of the pump, but it gets really unhappy when it goes to the other side and it instantaneously sees pressure. It's not an explosion that occurs, it's an implosion. As studies have shown that the force of that implosion is not measured, and you're talking about against the sides of the pump on the discharge side of the pump, it's not measured in pounds of force per square inch, it's measured in tons of force per square inch. Be very careful about cavitation. I've been to plants where the pump is cavitating and it's nearing the end of the shift, and the production supervisor will say, I'm just going to let it run. Because you see, I'll make 100 grand in the shift and it's only a $4,000 pump. Don't be fooled by that. Cavitation is a systemic problem. The little pieces that are being blown out of the hydraulic pump by this implosion are going down line, which means you're in the farming business, because every piece of contamination that goes down line is an abrasive seed and its growth is exponential. Today it's 1, tomorrow it's 10, the next day it's 50. So the first question we have to ask if we're going to let a pump go or just run it into the ground is, number one, can it cause an incident? In other words, can I lose control of the machine? Will I lose brakes? Will I lose steering? That's the first question. It's not about production. The first question is, will it hurt somebody? The second question is, if the pump is worth $4,000 and the hydraulic system is worth $150,000, I think you're going to be making a really bad decision by saying, well, I'm going to let it run to the end of the shift. All right. To make cavitation easy to understand, this let's say the workbook that comes with this particular trainer has 4 activities. Number one, we start it up and we get to know the patient. In other words, this is a gear pump, 1.8 gallons per minute. And I'm going to show you, the first thing I'm going to show you when I started is how to establish the point of reference. We know by rule of thumb the maximum is 8 inches of mercury, but we will very quickly figure out the point of reference. Then we have the ability, since we are monitoring everything here and since the whole hydraulic system is transparent, we can see the oil. This is the intake. This is the return. And we've got the larger diameter transmission line is the intake to the pump, transparent. The pressure line is also transparent. Let me just add something here quickly. I had a gentleman who took a photograph of this in a seminar and he went back home, back to school. And I really appreciate people that try really hard to build their own stuff because we're strapped for cash. I'll give you the drawings for this thing if you want to build your own. But No, I don't have pressure in the tubes. Hey, Rory, how do you keep the pressure in those tubes? I don't have pressure in the tubes. Gee, I wish I'd known because I just blew the one I built up. So don't do that, folks. I'll help you. If you don't have enough money to buy one, then you just basically build one and I'll help you. So here's what we're going to do. We got a flow meter. We got a vacuum gauge, 4-inch vacuum gauge. We got a pressure gauge. We got an ambient and oil temperature gauge. Then we got a valve here that'll allow me to let air go into the intake of the pump. I got a valve here that'll allow me to starve the pump. So that would let's say that would be low oil level starvation. Let's say a plugged screen, wrong viscosity. And then I can make pressure with this guy right here, on off switch over there. So I'm going to do 4 things right now. 1, I'm going to start it up and get to know the patient. 2, I'm going to do high inlet restriction. In other words, I'm going to simulate cavitation. Next, I'm going to go aeration, and then I'm going to show you what happens when the oil drops in on top of the oil in the case of a case drain line. First thing, safety first. Let me put my safety glasses on before we start it up. Even though all the pressure in this unit is behind the panel. We just want to be careful. All right, so I'm going to start it up. All right, now it's going to settle out in a second. Interestingly, I can see here I've got 1.8 gallons a minute flowing through these lines. In other words, again, what's interesting is you cannot actually physically see this flow. You don't want to see flow. Flow, if you can see it, it's turbulence. You don't want that. You want laminar flow. The other thing you'll notice is that every 60 seconds, I'm exchanging in this hydraulic reservoir 1.8 gallons of oil. So if every engineer could look inside the reservoir when they build a machine, they'd be able to see that there's some issues with the way things are working inside the reservoir. This also shows correct baffle design. I'm not going to go into that because that's part of reservoir design. But as we can see here, that's my return line here. This is my intake to my pump. I've got a breather on the reservoir. Remember, we needed to get atmospheric pressure in here to push the oil into the pump. All right. So now, my inlet restriction right now on this gear pump is 4 inches of mercury. So my ambient temperature is 84 degrees Fahrenheit. My oil temperature is 83. So it's only going to get better. I mean, if it goes up to, if I wait long enough to go to 135 degrees Fahrenheit, this is only going to get better. This is going to probably go down to 2.5. The lower, the better, but it has to be from a point of reference, which I'll explain in just a moment. All right. Everything's in perfect working condition here. So now let's go ahead and ramp the pressure up because cavitation, the noise of cavitation, of course, is sort of set by how much pressure you have in the system, because the higher the pressure, the more intense the implosion, and therefore the more it's likely to scream. I'm going to go up to 700 psi. All right. And now I'm going to replicate a plugged screen. I'm going to close this valve, and the minute I start to close the valve and create a higher inlet restriction, the inlet restriction is going to climb on my gauge. Here's what's really interesting. Remember what we said about the definition of cavitation, the formation and collapse of gaseous cavities in the liquid? Watch what happens when I reach a threshold inlet restriction where it all of a sudden comes to pieces. In other words, what I mean by that is the dissolved air comes out of the oil. Full-blown cavitation. Let's do it. So I'm going to slowly close this. The vacuum gauge is going to start to climb. And if you look at the intake right here, you will see the dissolved air here in a moment start to come out of the oil. There it comes. I'm in full-blown cavitation right now. Dissolved air out of the liquid. This is cavitation, the formation at the intake and collapse on the discharge side of the pump of gaseous cavities within the liquid. My inlet restriction is way up there. I mean, I've taken it well over 15 inches of mercury just to make the point. But that, my friends, is full-blown cavitation. Now, let me just tone it down for a minute. Let me just turn it off for a minute to explain something. You'll notice something interesting about cavitation, because there's folks who will look at the sight glass in a tank and they'll say, it's aerated, it's got foam in it, it's cavitation. No, it's not. You can see that. Notice that even though the dissolved air is out of the oil on the inlet side of the pump, when it goes through the pump, comes out the other side, it goes back into suspension, it's gone. There is no evidence of cavitation on the discharge side of the pump or in the reservoir. So don't be looking for foam, there isn't any. This is cavitation. If you see foam, that's probably pseudo-cavitation, the word pseudo false, because aerating the oil has got nothing to do with a liquid's vapor pressure or the entrained air in the oil, the dissolved air in the oil. So it's not cavitation. And that's why it's really important, don't you think, to have a point of reference? Because now I know we established our point of reference at 4 inches of mercury. So for the rest of this trainer's life, at this altitude, with that temperature, it'll run at 4 inches of mercury, which means if I came to this trainer next month and it was either lower, let's say it went to 3, or let's say it went to 5, I would know there's a problem. Because if it goes down, it's bad news. See, lower is not better when you have a point of reference, right? If you read a book on inlet restriction, it'll say the lower the inlet restriction, the better. Well, that's true. If the manufacturer of this pump says the max is 8, it can be anything below 8. It can be 1. But lower is not better if I don't have a point of reference. Let me show you why. So let me start that again. All right. So here's a summary. I restricted the flow, replicating an overspeed condition of the pump, replicating its plug screen. The dissolved air came out of the oil, went through the pump, imploded, cavitation. High pressure is going to start to peel out the parts of the pump because as you're imploding in the pump, it's just beating it to death. All the pieces are going down line. It's a systemic failure. I saw no evidence of cavitation in my pressure line, and I saw no evidence of turbulence in my reservoir. Now, watch what happens when I let air go into the intake of the pump. So let's replicate a leaking shaft seal on an internally drained pump, a low oil level. This is now pseudo-cavitation. Watch the difference. I'm going to open this valve and allow just a hairline crack, a loose fitting, a hairline crack, and I'm going to let air go into the intake of this pump. The first thing that I will see is my inlet restriction is going to go from 4 inches of mercury down, which means in this case, lower definitely isn't better. So let's do it. I'm going to open this valve. There goes my inlet restriction, and you'll start seeing the air coming in right here. Now, there it comes. I'm now going to aerate my entire hydraulic system. So the air's coming in there, it's going through the line here, and in a moment it's going to look as though the oil is actually boiling. As it comes through the return line, so it's going through the filters, through your valves, through the whole system, and as it comes through the return line, it's going to look as though the oil is boiling. Notice, it's going to aerate the oil and form a cloud of air across the top. Always starts at the top and goes down. Now, bear in mind, of course, what you're seeing in the reservoir represents all the oil in the whole hydraulic system. This is not just localized to the reservoir. This is wherever there's oil in the system. All right, so let me just shut this down for a moment. In my opinion, pseudo-cavitation is exponentially worse than cavitation. Here's why. Oil has 4 purposes. Transmit power with oil. Number 1. Number 2, I lubricate. 3, I seal clearances. And 4, I dissipate heat. Well, when the cavitation occurred, I had localized damage in my pump relative to the pressure. And I fed contaminants downline, which is undesirable, of course. But I didn't affect the purpose of the oil in the system. In other words, of course, I lost pressure and I lost flow because cavitation will yield that. And by the way, and that's something I'm going to back up on here in just a minute. I often ask students, have you ever tested a hydraulic pump before? And they'll say yes. Some will say yes. And I'll say, what did you use? And they'll say, I used a flow meter. What else? Pressure gauge. What else? Nothing. Cavitation drops the flow. Cavitation drops the pressure. So in other words, isn't that an incomplete test if I don't check inlet restriction? All of those elements that deliver oil to the pump could affect flow. So how many pumps, let's say, let's just ask this hypothetical question. How many pumps have been replaced over the years because I had a low flow rate, but it wasn't because their pump was fine. It was because there was a problem on the intake side of the pump, which I never monitored in a pump flow test. So all of the elements that affect flow output should be monitored on a pump flow test, meaning we need 5 pieces of diagnostic equipment on board. All right, so back to the purpose of the oil. As you can see, this foam, you can't, first and foremost, you can't produce power with it. Number 2, you are definitely not going to be able to lubricate with it. 3, you're not certainly going to dissipate heat with it, and you're certainly not going to seal clearances. So this is a systemic disaster in a hydraulic system. Foam in the sight glass needs to be mitigated instantaneously. So as you can see, the condition of the oil, because I've now aerated the oil. So once again, let me just start this back up again. All right. Cavitation. Let me do a summary. First of all, we got to know the patient. Everything was normal. Our inlet restriction was 4 inches of mercury. Second, we simulated cavitation. I restricted the flow going into the pump, allowed the dissolved air to come out of the oil, and I had cavitation, which was localized to the pump. As soon as the oil came out the other side of the pump, the problem disappeared. I'm not saying we don't have a problem because pieces are going down line. I'm just saying there's no evidence of cavitation. I did lose pressure and I did lose flow. Second, I went to aeration. Back to normal, I opened the air inlet valve and I fed just a small amount of air into the intake of the pump. Inlet restriction went down, and of course, as you saw, it started to perpetuate aeration, contaminated my oil and my entire hydraulic system with air. Terrible condition. All right. Now, finally, what happens if, by rule of thumb, there should be no oil, a return line dropping oil in on top of oil? It's against the rules. Some manufacturers are so bent on keeping case pressures down on pumps and motors that they will actually drop the oil return lines in above the oil level. You can't have any flowing lines putting oil in above the oil level because it will create, for the life of the machine, it will just perpetuate air. Let me demonstrate that for you. This simulator is designed so that you can drop the oil level in real time. So let's do that. I'm going to open a valve here, and I'm going to drop the oil level. This is the return line here. The white tube is the return line. And in a moment, I'm going to start it up, and you'll see what happens when you drop oil in on top of oil. This is likely to occur because, rule of thumb, we should be putting all our return lines 14 to 16 inches below the oil level. What if you neglect the oil level? And now you have oil going in on top of oil. These are situations that are extraordinarily bad because, remember, no matter how you look at it, cavitation, either cavitation or pseudo-cavitation, is a systemic problem. It invades the whole hydraulic system. All right, oil levels dropping. Let's start it back up again. 2 things are going to happen. One, you're going to see a tremendous amount of turbulence occur because I'm dropping oil in on top of oil, and bear in mind, I'm only dropping in 1.8 GPM. And the other thing on the left side, I'm going to let you see what a vortex is. So this is going to stage down to study those 2 phenomena. What happens when you drop the oil in on top of oil, number 1, and what happens if you're dangerously close to intakes, which is a big problem in a lot of machines. Let me show you. So I'm going to start it up again. My intake is almost out of the oil. Sorry, my return is almost out of the oil. About a quarter of an inch to go. Notice in this area here, you'll just get a huge amount of turbulence. And of course, as you well know, or maybe not, this is going to start creating an air condition. It's going to introduce air into the system, and you're back to square one, back to pseudo-cavitation. All right, so now we're just about out of the oil now. I'm now dropping 1.8 gallons a minute in on top of the oil in the reservoir, and you can see the amount of turbulence it's generating within my reservoir, and that is going to generate air, which is back to, as we said, pseudo-cavitation. It's starting to aerate the oil. On this side, I'm now creating a vortex. So here you can see the vortex created, which is a problem, obviously, in the design of many machines. All right, this, as you can see, we're back to square one. Highly undesirable situation. All right, so once again, what did we do? What we wanted to see is what happens when you drop oil in the top of oil. This is a common problem in design because you have to realize large cylinders consume a large volume of oil. Because of the area difference of a cylinder, when you push your rods out, you get to take a great deal of oil. Think about a telescoping cylinder. It's going to eat oil. So your oil levels are coming down, down, down. What about accumulators? They're going to consume, depending on the size, depending on how many, they're going to consume oil. So if an engineer doesn't get it right to where he or she has calculated the volume of the reservoir to accommodate the volume of oil that is being pushed, that is being consumed by those devices, you can encroach on your intakes and you'll never know. People will become complacent with these kinds of problems. So as you can see, this really helps me understand not only how the hydraulic pump works, but it also helps me understand all of the problems we are seeing on the intake of hydraulic pumps. So isn't it disturbing, though, that, and you know, I'm talking to a lot of people, a lot of instructors. Do you know of any instances, in fact, I'd really like to get this feedback. Do you know of any instances on any machine, because I mean, I'm sure a lot of you have come from dealerships, where on a routine maintenance basis, they've put a little connector in the line, one of those cup connectors, what I call connect under pressure connectors, where they are non-invasive. How many pumps have you seen with those little connectors that enable me as a maintenance professional to go in and check inlet restriction? That's the first challenge you're going to have. Second challenge. Has the designer made it possible for me to put the pump onto full stroke to make this observation? In other words, I can't be in the engine compartment while the operator is operating a front-end loader, and I'm running a pressure compensated pump or a load sensing pump. Shouldn't I be able to bring the pump onto full flow, because then I can actually see what the worst case scenario is? In other words, be careful of this. Sometimes in perhaps you're troubleshooting a machine, you'll hear the operator say, it's really funny, the pump doesn't make a noise when I run the hydraulic motor, but it makes a noise when I run the cylinder. That's a consumption-based problem, meaning this. Let's say you've got a 50 GPM pressure compensated pump or load sensing pump, and let's say to run the motor you only use 10 out of the 50, and let's say you've got a partially plugged screen. Well, 10's okay for a partially plugged screen, let's say, but the cylinder wants 45 out of 50. See, it'll only cavitate when the cylinder rod's moving, but not necessarily when the motor is running. The student activity book for cavitation comes as a 4-part, extremely comprehensive overview of cavitation. Now, just for the record, sometimes when we bid hydraulic trainers, we're asked to put restrictors on the intake of our pumps. Can you just switch over to here for a minute? Okay, this is the Model 102 pump, and it's rigged completely for checking inlet restriction on the fly. So you've got a vacuum gauge down here, and you can just screw it straight in, which is how all pumps should be rigged, in my opinion. Okay. It's also rigged to do case pressure testing, etc. So the pump comes out so that we can get right onto it one-on-one. Okay, and of course this is a pressure compensate pump, so we can run both environments, both fixed and variable displacement. But this gives us a great opportunity to get to know the patient, to get to look at inlet restriction on the pump. So that's basically what we're looking for. We're looking for this to be on all hydraulic pumps so that a maintenance professional can go in and check inlet restriction on a routine maintenance basis. But at the same time, if it's a variable volume pump, I need to be able to get it onto full flow condition so that the inlet restriction is checked at full flow. So in other words, the maintenance professionals would have a little connector on their gauges. This is a 0 to 30 inches of mercury is what we check inlet restriction with. And when we're checking inlet restriction on a pump, we also want to look at RPM. So we want to go and check RPM because RPM, especially on a diesel engine, could be a factor. If we replace a PTO, if I get the gear ratio wrong, this could create a problem for me. So my vacuum gauge is a very, very important part of my testing. We will not, when we are asked in bid to put a restrictor on the intake of the pump, we're scared to do that. This is a very expensive pump, folks. It's a pressure compensated variable volume axial piston pump. If we put a restrict in here to sort of, because that's asked sometimes in specifications because some of our competitors do that, but we can't afford to do that because what if a student closes it off somewhat and forgets about it? These students are learning. They can forget things. So we can't afford to do that. So if we come back at you, if you ask for a bid and we come back and you say, sorry, we can't do that, don't hold it against us, folks. We're just worried about the fact that it can cause a problem down the line, a very expensive problem down the line. We don't want that. So we would rather take, first of all, I mean, if I'm restricting flow, you're going to make a noise. So that what they'll do is they'll put an air inlet valve and they'll restrict the flow. Then they'll say, listen to the difference between the two. Well, folks, I'm sorry, I can't. I would walk out of that training session and would know nothing about inlet restriction. Cavitation, because I can't remember the noise differences between aeration and cavitation. It just wouldn't work for me. So that makes it really, really convenient for, and I encourage those instructors who are specifying training simulators. It doesn't help to put the hydraulic pump inside the tank. Because you'll notice I see a lot of, and I'm not standing here berating my competitors by any means. That's not my point. I think we're looking at the learning experience. If I put the pump down in the oil, I take all that opportunity for the student to learn flow testing, et cetera, away from the student. I want the student to be on the pump. So as you can see, I can check inlet restriction, I can learn what it's about, and I can do it without putting a drop of oil on the ground. So this is very important. And so let's summarize. Let's go back to this guide, summarize. What we first and foremost started out with is we showed you how the intake side of a hydraulic pump works. And we said it's absolutely critical that I get to know what the point of reference is. With that point of reference, we went and started up this simulator and we demonstrated 4 things. 1, we got to know the patient, meaning we got to know what the point of reference is, the flow rates, the pressures, etc. Then we said, let's start out by looking at cavitation. We closed the valve to replicate, let's say, a plugged screen, and we saw that the dissolved air in the oil came out of the oil, and it was evident on the intake side of the pump. It disappeared on the pressure side of the pump when the implosion occurred, and it went back into suspension. Drop pressure, drop flow, which means if I have a pressure decrease in my hydraulic system, one of the suspects would be the intake of the pump, because everything we do in troubleshooting is symptom-based, right? All right, so we looked at that. Inlet restriction went up beyond the max recommended by the manufacturer, and we saw that the reason was because we restricted the intake. All right, so we got to know the patient, we looked at cavitation. Then we said, okay, let's see what happens when we let air go into the intake of the side of the pump. We opened the valve. air went in and it infused the whole hydraulic system with air. And again, we lost pressure, we lost flow, but we lost everything. Because now that foam you see in the sight glass or you saw in the tank here is prevalent everywhere. By the way, some of you might be looking at this saying, well, how do you fill that thing back up again? Well, we made that easy too. So all you have to do is go to the back of the simulator, close a valve, open another valve, and it'll self-fill. So you're ready for the next activity. All right. So any questions anybody has? I'm pretty much done with the presentation. I thank you for your time, and I thank my friends at Dactic and Consulab. And if you have any questions at all, please fire away.
Rory, I do have one here. This is actually a little bit from previous, but he says, can you give specifically the name and material of gloves to work with high liquid pressure injection systems? All right.
Thank you for the question. I will give you the name of a company. I don't endorse any companies for these products because I don't know them at all. I know specifically of a company called Pirtek, P-I-R-T-E-K, home-based in England. They have facilities all over the United States, apparently. These folks specialize in mobile hose repair services, and they apparently have a patent on a glove that is like an armor. It's got armor in it, but again, it has some issues with respect to where it does and does not protect. And also, it has, from what I understand, it is severely restrictive. Okay, that's just what I understand. So please, anybody interested in that, please have that conversation with the folks at Pirtek, get the assurances. And, you know, I'm all for, first of all, let's mitigate the problem. Let's build a hydraulic system that you don't have to crack the lines so we mitigate the problem. But I would recommend you contact, I'm sure the Pirtek folks will be they're very nice people. I'm sure they'll be very, very happy to tell you all about the glove and what its capability is. I know of no others. That's the only one I know of. Hopefully that answers the question.
That sounds great. So we've got some other feedback that just says this is incredible and some other positive things being said here, but I don't see any other questions right now. We are a little bit over time, which is fine since you're the next presenter. But I'm going to go ahead and take a 10-minute break here, everyone, if you're needing to hit the restroom before we start on hydrostatic drives. In the meantime, go ahead, Rory.
Sorry, I'm just finding out how far over time we are.
Oh, not much. This was 45 minutes, right?
Yep. Oh, I'm sorry. I just blew that one. I thought I was going for an hour. Sorry.
That's not a problem at all.